Okay, welcome back. This is our fifth panel of next generation electrochemistry, a panel on local phenomena in electrochemistry. Again, a reminder that this is our sixth edition, and this is an online event that is managed by University of Illinois Chicago. This is the second event of the day, and it's going to be another panel. It's the last panel of the day. We'll have one more event, but it'll be run differently, and we'll get to that when we get to that event. But this one is another panel discussion. We have four experts in the area of thinking about local effects in electrochemistry that are going to share their thoughts. We'll go through opening statements, 5-10 minutes. Their charge is to go over critical fundamental questions that they see on the topic that we're discussing. And then we'll start a discussion. And again, as usual, we have our group of students and postdocs in the Zoom call. And then we're going to give them the opportunity to start asking questions to the panel. We are live streaming through YouTube. If you're on YouTube, there's a chat function. You can put your question there. We're monitoring that, and we'll transfer the question to the discussion if we are able to. We're going to run for 90 minutes. The panel this morning ended up going a little over. But we're going to enforce the 90-minute requirement like we did this morning in the end, so that we respect the time of our panelists, who surely have a lot of other meetings that they have to get to today. For those of you that are going to be our panelists, it is very important to follow the NGenE tenet of focusing on the gaps, focusing on frontiers of knowledge, making sure that you share with the next generation what you think are going to be the problems they're going to encounter if they continue to do research in electrochemistry. We've had already some elements of controversy, and I think that that is good. The students are told to challenge the faculty, and that has led to some forms of controversy, the faculty with each other as well. This is your opportunity to expand your message beyond your group and influence research that happened elsewhere. We've already focused quite a bit on the on ideas of thinking critically and articulating proper concepts from a basic perspective to make sure that we advance knowledge. To the attendees, you know the drill by now. You've been great. Keep getting involved. Some of you have been asking questions on topics that are going to come up again, but this time you're going to hear about the exact methods that are used for some of these from an analytical perspective. So it's your opportunity to ask your questions again. As usual, post in the chat if you want to ask something. You'll be given the floor. This morning we had a parallel discussion in the chat. That's totally fine. You can engage that as well. Be challenging and definitely think broadly, like you've been doing so far. Okay, so I'm gonna release control, and our first panelist in the order that we agreed upon is Nina Balke from right now from Oak Ridge National Lab, but in just a few weeks she's moving to North Carolina State University. Nina, your turn is up. The floor is yours.
Thank you, Jordi. Thank you so much for the invitation to speak here. I think this is a really interesting format. I try to keep my slides very basic and quick and get to my main point. First of all, as like a small introduction, why and how do we track local electrochemical processes? And I think the choice of this panel is excellent to show you different ways of how to track local electrochemical processes. So I come from a field where we think about how to get into this corner of the Ragone plot. I've mostly worked on capacitors, a little bit in batteries, supercapacitors. So we want to store more energy and do it quicker to get up here. And so one big research interest of mine is looking at strain. And I tried really hard to make this not about strain, but strain also gives you an opportunity to track local electrochemical processes. So I want to talk a little bit about it. First of all, if you ask the question how to track processes, that depends on the length scale you want to look at. So we have the electrode, you have your typical macroscopic characterization techniques. You have your atomic scale, so there's beautiful TEM and SCEM work going on. But then you have like this length scale in between, which is a little harder to reach. And so here I'm mostly doing atomic force microscopy, where you can look at or cover the range of tens of nanometer to hundreds of micrometers. So it's easily to map across grains and grain boundaries, which is really interesting. And AFM itself cannot measure the ions directly, but it's sensitive to mechanical properties. So any type of volume change, if ions get inserted, changes in mechanical stiffness, those methods or those properties can be mapped on a local scale, and they are indirectly linked to ion intercalation. And we can use those to look at local insertion kinetics. That of course requires that you understand the interactions between the electrolyte and the electrode in terms of how it affects mechanical properties. And I want to show one example of why it's really important to know about the local variations, the heterogeneity of ion intercalation. Here I'm showing an example of a layered MXene material where we played around with co-ion intercalation. So if you try to get magnesium into this electrode, it doesn't really want to go in much. You have a relatively low amount of stored energy. However, if you pre-cycle it with potassium and then you exchange the potassium with magnesium, you really increase your energy storage. So we're pushing along the horizontal in the Ragone plot, and the question is, where does this come from? Why do we have more energy stored? So in this particular material system, if ions get intercalated, it changes the interaction strengths between the individual MXene sheets. And this can be mapped with AFM by mapping the local stiffness. So here we have Young's modulus. And if I insert magnesium without this pre-treatment of potassium, everything, so we at zero open circuit potential, everything would be green. Now you see, after we intercalate ions, we get this increase in stiffness. This is where the ions go, and you see local heterogeneities. However, if we pre-cycle with potassium, you see it's much more homogeneous response. That means magnesium now goes everywhere, and before there were about 20% of area where magnesium did not go. The reason of that is still under investigation, but it shows you that we can explain this increase in capacitance, which is about matching the area fraction here of the electroactive material fraction. And looking at scan rate dependence, it shows you, indeed, you don't change the intercalation kinetics, but really just the amount of potassium which goes in, which is because of the increase in active area or area which can take ions in. And so I was really intrigued by Jordi's homework to come up with like a burning question. And so this is a question I'm trying to answer, and I have this is all speculation, and I hope it can trigger some discussions later on. But my big question is if local electrochemical processes can influence each other, or are they totally independent of each other? And strain gives you a good example of discussing this. For example, if you imagine you have like individual grains, for example, lithium cobalt oxide, and because of local field enhancement or grain orientation, let's assume the lithium only goes in one of these grains, or goes in there first. This grain will contract in the case of lithium cobalt oxide. So now it's starting to strain the neighboring grains. If they're pre-strained, this could result in local dead zones. Not that I've seen that, but that's a speculation, the question if that happens, which can then lead to reduced charge storage or modified intercalation kinetics. And also it brings in gradients in strain and gradients in lithium ion intercalation. So you also have to worry about lateral ion flow, which could result in a competing ion flow. And with that, I just want to leave this up, and I'm happy for the next person to take over.
All right, thank you, Nina. So our next panelist giving his opening statement is Joaquín Rodríguez-López from the University of Illinois at Urbana-Champaign. Joaquín, floor is yours.
All right, awesome. So first of all, thanks for the invitation, Jordi, and I'm super happy to be with all of you here in this edition of NGenE. I've been participating in several of these NGenEs before. This is my first online, but hopefully we have a good discussion today. So my presentation, and if you take a message from me today, is to think small, especially if we're dealing with electrochemical measurements. So I am an associate professor in an analytical chemistry department, which means that I really like to detect things and I really like to figure out ways in which to look at electrodes. Specifically, one of the things that we tackle in my group is electrode heterogeneity. And this is something that you all know. You have looked at your electrode, you have seen that there are differences in the different areas that you explore, in the way that you deposit an ink on your electrode, in the way that your electrode evolves when it reacts. And so these are the types of things that we really want to look at. Oftentimes, when we measure voltammetric signatures, or when we measure impedance, or when we measure properties, we average them over an entire area, right? That is comprised by the area of your electrode that is exposed to electrolyte. But there's so much richness, right, in things like, differences in the local structure of the electrode. When you have composite materials, where, as Nina was talking about, you may have different grains, you may have different grain boundaries that are formed between the materials, or that you have discontinuities in the material. What happens when you have not only these things happening within the material, but on the material, right? When you have things like interfaces that form. So here's an example, for instance, of a molecular interface that forms when a redox species forms a film over an electrode, and this film can actually come and go, right? But we also know about irreversible interfaces. If you do energy storage, you have heard about the solid electrolyte interface. And so you can also have things that passivate your electrode in an irreversible way, in which understanding how these interfaces grow and how they age is really critical. And so the point in here is that we definitely need techniques and ways to think about this site-dependent reactivity, right? Where you have different structures that form on your electrodes. But there's also other things that are really important, right? Oftentimes, when we talk about electrochemistry, we can be talking about different components of the electrochemistry. So it's not only about looking at little things that happen in your electrode, it's sometimes also about figuring out what are they affecting. Are they affecting the ion transfer processes? Are they affecting the electron transfer processes? As Nina was saying, right? What happens, things happen at the micron scale and things happen at the nanoscale. But there's also like this mesoscale, right, where there could be other interactions that we care about. And so for this purpose, the think small philosophy goes into thinking about small electrodes. And the small dimensions of electrodes can imply having something like a microelectrode. So here is one of the original reports in analytical chemistry in the mid-'80s by Stanley Pons and Martin Fleischmann, and I'll give you brownie points if you tell me what else these two did. But suffice to say that at this point, they were really interested in using small electrodes to look at these heterogeneities that I told you about. One of the very first things that they tackled, for instance, was to grow, to have single nucleation sites, right? So they were also saying, look, a surface is heterogeneous. How about we make an electrode that is so small that we have one single nucleus forming in there? And this kind of thinking can be explored in so much more detail, right? So we use these small electrodes not only to think about having individual entities, right, or individual processes happening in your electrochemical interface, but as I mentioned before, to develop analytical strategies that can help you focus on individual elements on the surface. So this is the concept about the scanning electrochemical microscopy. You heard a little bit about that already in the previous panel, so I won't elaborate too much on it. But the point in here is that the heart of all of this is to use small electrodes to look at highly localized processes on your surface. Whether these are things like looking at the evolution of products, to look at redox reactivity through these kind of boomerang techniques, right? These redox shuttling techniques, or even looking at what happens on surfaces, right? Absorption at surfaces. And of course, not only generating nice pictures, but also analyzing them quantitatively. So my group, just to give you some examples of where we're taking this whole concept of looking at the locality, we're really interested not only in being able to measure things at the local scale, but also to decouple processes, electronics versus ionics, to correlate, to use these small techniques, not only to look at the local rates, but to understand what is happening with the material. And we do this by combining these scanning probe methods with spectroscopies. And also to think about how can you design electrodes so that you can look at these local effects. So for instance, there's a concept that we have explored in which, we want to look at surface processes or interfacial processes, and where we have asked the question about what if you take a bulk material and you start to thin it out, thin it until the entire behavior of that substrate is reflecting the behavior of an interface. So using small electrodes, confining electrodes to small dimensions, combining those small electrodes with other means of measurement so that you can understand how the local reactive properties are correlated with the structure and with other properties. And so these are just very quick examples of this. So this is an example of our ionic probe, right? Where we use a really, really tiny mercury droplet to look at the intercalation, the insertion and deinsertion of lithium ions on an active electrode. In this particular case, when we're forming an SEI, we can see the fluxes of ions coming in and out. So this is an example of decoupling the electrochemistry that is happening. Our SECM Raman work, where we can take simultaneously information, we can take images of the local redox reactivity by shuttling a redox mediator between a tip and a substrate, and at the same time doing Raman spectroscopy at every pixel so that we can make correlations like this, where we can correlate the rate of electron transfer to the electronic structure of the electrode that you're seeing. And also using ultra thin electrodes, for instance, to look at interfacial processes, like in here comparing the rates and the properties of lithium insertion versus potassium insertion. Nina was talking a little bit about that, about how important it is to design or to figure out what the reactive conditions on which you form interfaces is, how it conditions reactivity. And this is yet again another example of that. So just to close my discussion, I just want to mention also that all of these cool techniques about thinking about small electrodes to look at the reactivity of your electrodes are not confined to metallic electrodes, to platinum, to mercury, to things like that. In the morning, you probably heard about using pipettes for looking at local phenomena. And this is a beautiful example from the Kanan and White group about how this can be used, for instance, to look at reactivity across boundaries, across brain boundaries, as Nina was mentioning. How you could also couple, it's not only about the spectroscopy and electrochemistry, you can do things like mass spectrometry, as is this case, right, where you can make these push-pull probes that, where you can look at the local electrochemical reactivity, but also at the mass spectrometry, and how this can even be taken like completely to different areas, right? This is a very interesting paper by the group of Catherine Jung-Johan, who has done also transmission electron microscopy. You don't need to do SECM to look at this, but the important point in here is that using small electrodes where you can understand quantitatively what the current is telling you, and at the same time looking at the reactive evolution of your substrate is really key. So pointing here, small electrodes, understanding the currents, discerning the different processes, a really important direction. And so, as Yoda would put it, being small doesn't necessarily means nothing. It's good. We can be like Yoda at doing electrochemistry. I would be happy with that. And of course, it's up to you to show how that can be done. And with that, I'm open for discussion.
Okay, Joaquin, just so you know, I put a prompt for the brownie points, and I think there were a couple of responses if you want to check the chat and see if anybody got the brownies. Maybe you have to go and buy them at a bakery.
Tommy gets the brownie points.
Okay, next up in our opening statements is Debra Rolison from Navy Research Lab. Debra, whenever you want, you can start sharing and see if it works. I'm ready with the backup in case it doesn't.
That's right. Currently, it says I'm disabled.
Oh, yeah, because it doesn't. That's not right. There you go. Okay, I'm going to stop my screen. Oh, yeah, you're good now. You should
so
be able. Yeah,
here I am. So Joaquín took a small, and as a trained electroanalytical chemist, I do appreciate the quantitation of near single events, but to be technologically relevant, you've got to get them to work together and give you, amps. So I want to talk about controlling local events at electrified interfaces by distributing them, which means you have to think about how you wire your electrons and your ions and your molecules. And that's a pretty easy thing to do if you're working with architected electrodes. So just a little step back. To me, all electrochemical technology requires optimizing electron transport, ion transport, molecular, i.e. mass transport, and remembering your local current exchange densities, your electron transfer kinetics. And I like to use the fuel cell as an example of that. Of course, fuel cells run on any fuel as long as it's hydrogen. So let's go look at the anode where we're oxidizing the hydrogen. And that is still typically nanometric platinum supported on carbon. And this is an image we've taken of nanoplatinum on Vulcan carbon. And that's the microscopic view. But if you go nanoscopic and think about what's really happening when everything collides, you have to have electrons handed off after the platinum oxidizes the hydrogen through an ad hoc carbon wire to go back to a current collector. You have to get a proton out of there, so you have to have some protonic conduction, whether it's ionomer or liquid, away. And of course, you have to consider what are your heterogeneous electron transfer rates as the hydrogen is adsorbed and oxidized by the platinum. So there's a lot happening in a very small interface. And even in batteries, to me, that three-phase bottleneck still applies. In electrochromic, it still applies. You have to think about how you're fluxing your ions and your molecules to that active electrified interface. You have to think how you're moving the electrons there and away. And of course, in the battery world, we're very much concerned with what's the solid state ion transport. And we've lived making these devices in what I call the glop and slop masonry approach, typically powder composites or inks. And so if you think like an architect, that to me allows a more optimized consideration of all of these per second functions we need. And so I'm coming at that from an architectural. In aperiodic architecture, we use aerogels. You don't have to use aerogels, but the important thing about an aerogel feedback loop with electrochemistry, when you've got an electroactive network in there, is that aerogels are scalable to any length size, unlike the periodic templated systems, which typically are supported thin films that are a few microns thick. Because you've got co-continuous 3D open networks of void and solid, those molecules can come through large-scale aerogels close to open medium diffusion rates. And because you're often coming from a benchtop low temperature route, you can actually start to probe what happens between an order-disorder combination in the solid in your system. So we love aperiodicity. It's not a photo op, but it is technologically very relevant. And as I wrote in 2003, architectures contain a lot of nothing, and that is a key part of what makes these things work. So as we learned more and more with aerogels, we decided to step back, if you will, into even a bigger space and attack a decades-old problem with alkaline zinc-based batteries. You're in water, you've got a high pH alkaline electrolyte, you've got a gelled or powder composite zinc particulate electrode, and it's great as your manganese oxide primary, very safe, environmentally benign. But if you try to cycle that, you start to form dendrites that can pierce the separator. Now, unlike the lithium world, it just loses voltage. You die with a whimper, not with a bang. But because we'd already understood the importance of these aperiodic architectures, we fused those particles together to create a sponge. So now this sponge is a macroscale object, and you've always got an inner core of zinc metal all the way back to the current collector. So the volume is wired beautifully in a way that you just can't accomplish with most powder composite structures. And so you could cycle that all day long, and you do not make dendrites. So sponge goes in, sponge comes out, And no big surprise, we have a fair number of patents on that. And it has been licensed. But to prove to ourselves that our cartoon was correct, our design hypothesis was correct, we took a page from the lithium battery world where you want to make dendrites by looking at lithium versus lithium. So you can really hit it with respect to current, but you of course don't have much voltage across that cell. So we let that run for 3.5 days in this little plastic cap cell, just toggling the oxygen back and forth, zinc to zinc oxide, and looked at it 3.5 days later. And we were a good 7 times over the, at least a couple times over the critical current density to form dendrites for zinc in the alkaline electrolyte. And you look at the exterior and it has retextured, but you can see how uniform that retexturing is. And if you cross-section it, you see the same structure on the interior. And that's what wiring the electrons, having the electrolyte all the way through the volume of the electrode, you're controlling some very complex electroreactions, chemical complexations, precipitations in a way you just can't do with dissociated particles or even zinc foil. And these structures have no loss of mechanical integrity, no obvious shape change. We have never seen a dendrite, and we've hit some of these with 0.5 amp per square. And that uniform precipitation of the zinc oxide is why dendrites can't launch. No one site controls where the current distribution is and thereby gets the flux of the reactant that forms the zinc metal. So that confinement and that 3D wiring and having everything bathed in the electrolyte is why this works. If you make the void size too small, here we are on the microns, tens of microns length scale, you don't have enough electrolyte, you start to lose control. If you've got too much void, well, you don't have enough zinc to do what you want to do. And the reason zinc's important, we just published recently a study of the supply risk analysis done by the European Union versus the presence in the Earth's crust of some battery relevant elements, so pick your favorites. But of course, where you want to be is down in that green lower right-hand corner where, fortunately, that's where many battery things are. Lithium doesn't quite make the cut. Cobalt has its own issues, but of course, zinc and manganese and iron and aluminum and nickel, copper, those are our players. And if you then look at the system cost, and I will tell you right now, I don't care what your per cell energy density is, because most of us aren't working with a single cell. It gets stacked into many cells into a pack. So you need to know what your system cost is. And that's where lithium batteries lose out, because you have to put in all this thermal regulation and catastrophe management, and that adds weight and volume. So if you're looking at the system cost in watt hours, kilowatt hours per dollar, you see that the zinc-based systems are really where you want to be to get both the energy and the low cost. And to close out, I'll do another opportunity with zinc, but with zinc ion, again in 3D. So there's been a lot of publications over the last 5-6 years as people recognized you could step out of alkaline into near neutral aqueous electrolytes and do what was thought to be zinc insertion into lamellar oxides like manganese oxide, some of the vanadium oxides. And so manganese oxide in the lamellar form is a very good pseudocapacitive material, sodium ions in aqueous, lithium, potassium, things like that. But the thought was if you had the divalent zinc, it could go between the layers. So that was the hypothesis. And we've had a lot of work with paints that are about 10 nanometers thick of manganese oxide in that lamellar crystal habit inside high surface area carbon nanofoams, device-free electrodes because they're formed within carbon fiber electrodes. So no binder, no inking, no polymer, anything required. And because we understand the pseudocapacitance of these materials, we didn't just look at this with a zinc sulfate electrolyte, so there's no sodium in there, that's that blue curve. We studied it with sodium and zinc. And so if there's just sodium, it's strictly a pseudocapacitive voltammetric signature. Once you start blending sodium and zinc sulfate, keeping the concentration of the sulfate the same all the way through, you can see that you start to keep what looks like a classic Faradaic signature in there. And it's important to blend those electrolytes because you just can't keep much specific capacity per gram of manganese oxide. And I remind everybody, tell us what your per grams are, because the zinc just can't keep up. So by adding in the sodium, you're allowing the pseudo-capacitive reaction to kick in, so you can still get high capacity at rates that the zinc just can't keep up with. And we also introduced with this system a lesson learned back in the 90s from Brian Conway, who was using a three-dimensional analysis of impedance data for inductive effects in corrosion. Well, Jesse Coe, as a postdoc with us, flipped that on the axis to look at the capacitance. So now you've got 3D plots of looking at area normalized capacitance as a function of the frequency, as a function of potential. And if you've just got sodium in that aqueous electrolyte, you see that waterfall effect, what you expect to see from an electrochemical capacitor. When there's just the zinc and no sodium, you can see that Faradaic response as a function of potential. And when you start to blend them, you see you retain the Faradaic, but the real winner is a 6-to-1 sodium to zinc, where you've still got the predominance of that pseudocapacitance plus the Faradaic. And it's very clear to see that using this 3D Bode analysis. And we think that's a very powerful tool as opposed to the B analysis of voltammetric data, which is really an abomination. But once we started to analyze this distributed reaction system, again, we've got a macro scale thick electrode, binder free, and we could do the microscopy after we'd done as made, discharged, and then recharged. And you can see from the exterior of our carbon nanofoam paper that once you've discharged this system in the mixed electrolyte, you've put salt on the surface of the electrode. And you lose that when you come back. And on the interior, because we can cross-section these things, it's relatively free of the salt. So the hypothesis was always wrong. In these near neutral electrolytes, you're still inserting the proton into the manganese oxide lamellar material. And that, of course, creates a high pH interface distributed across that area. And that's what precipitates the salt. It's a zinc hydroxysulfate salt. And then when you charge the system, you, of course, are bringing the protons out of the oxide, and that allows that salt to dissolve. And to see if we could actually get honest to goodness zinc divalent intercalation into lamellar manganese dioxide, we've already reported the ability to take these 10 nanometer thick lamellar layers and do crystal engineering within a macro scale thick 3D carbon nanofoam. So we converted that to the zinc spinel, that of course was verified by X-ray diffraction, and did very much the same thing. Looked at it as prepared, looked at it as discharged, looked at it as recharged, and oh yeah, there's still salt there. So the original hypothesis was wrong all along. It is the still classic proton inserting into the oxide just as it does in the alkaline world. So our normal way to make technologically relevant electrodes is the composite. If you think like an architect, you can get the same types of weight loadings, but now as nanoscale thick coatings over high surface area, in this case, carbon nanofoam current collectors. You still have your macro scale electrical contact, but now you've got a good wire leading all the way through that structure. So you've achieved that wiring of ions and molecules and electrons in 3D. So the zinc ion highlights the issue going forward. You've got a good current collector wired in 3D. You've got a thin nanometric redox active coating that's going to be doing your reactions or your energy storing or your catalysis. But you still have to talk about the handoff back to that carbon. And as we all well know, carbon is not an ideal fast heterogeneous electron transfer surface. So yes, my friends, we're right back to chemically modified electrodes. Only we're doing it in 3D with a massive amount of electrode area. So you're not isolating a single unique site. It's going to be telling you things that you'd have to be blind to ignore. So our key question that I'll leave you with is, how can you improve that handoff back to typically carbon current collectors in most systems? Because if that's slow, that's going to impact your power. And if it's not, if you will, a good molecular orbital designed handoff, you can affect your energy storage. So Joaquín wanted you to think small. I want you to think wired in 3D and large. Thank you.
All right, thank you, Debra. So we're going to go to our last opening panel. You can start preparing your questions because we'll open the discussion next. I see that there's already some discussion that has started, so that's great. We'll have more after Reza Shahbazian-Yassar, who is at the University of Illinois Chicago, gives us his take on local electrochemistry. Reza, do you want to try sharing, or should I just go ahead and share from my computer?
Yeah, if you could, I will try to share. It was disabled. I don't know if you have given permission to share.
You should be okay now. You can try.
Okay, I'm not. Oh, okay, let's see. I'm still not able. Maybe if you could share it.
Yeah, I'll share it.
Great. Yeah. Yes. Okay, thank you.
Good. So you're on.
Okay, great.
Okay,
great. Thanks, Jordi, for the invitation, and it's great to be in this panel with the rest of experts and battery researchers here. I'm Reza Shahbazian-Yassar. I'm a professor in Department of Mechanical Engineering. My group mostly focuses on in situ electrochemical reactions inside TEM. So to some extent, you know, some of my work can complement the work of Nina and you know, some of the work that Joaquín mentioned in his presentation. So I'm at the University of Illinois Chicago, and we have access to state-of-the-art electron microscopy here at UIC, as well as we have a number of good electron microscopy facility at Northwestern University, that an Oregon National Lab that my group is trying to leverage for our work. If you go to the next slide, I wanted to share mostly about what we think is going to be, you know, at least my group is thinking that it could be important for a new generation of electrochemical researchers to think about. You know, in my group, we think that, you know, more emphasis should be given on the atomistic scales and understanding the nanoscale electrochemical reactions in order to be able to elucidate better how electrochemical reactions are responsible for battery performance, for its degradation, for, you know, how what are the mechanisms of ionic diffusion or so. So I think over this 30-40 years of a lot of battery development and work, this atomistic scale sort of work has been relatively maybe ignored or less emphasized, because it's usually very difficult to look into inside the batteries and look into electrochemical reactions at that level. But nowadays we have tools and we have capabilities to make this happen, and I encourage all the students to consider that. With respect to the type of work we do on in situ TEM, there has been a lot of improvement, you know, in the last 10 years in understanding electrochemical reactions, but I think we can do better. There are more and more capabilities that are being integrated with electron microscopes, such as energy loss spectroscopy, EELs, doing Raman, doing cathodoluminescence, doing SIMS. That these all can be integrated with the TEM study. So we are not just limited to some like typical bright field, dark field TEM images, and we can utilize this additional signal to understand better electrochemical reactions. Also, we need to do better job in doing nanoscale electrochemical cell development. If you want to look into reactions at atomistic scale, we need to have cells that allow us to have very high resolution both energy-wise and spatial-wise, and also allow us to do electrochemical reactions that are comparable with what we expect to see in the bulk reactions. Another challenge that we face, and we think that more efforts should be given in this direction, is related to beam sensitivity of a majority of materials that we deal with in the battery systems. For example, lithium is very light. The interaction with electron can result in totally different kinetics or maybe thermodynamics eventually. And therefore, we need to better understand the beam sensitivity of materials. So how we can perform better electrochemical reactions under electron beam conditions, that's another challenge. And these are some of the future directions that we should be thinking about. Fortunately, with the development of direct electron detectors, low dose microscopes, we think that this can be done better, and we can hopefully make a better quantitative correlation with electrochemical studies. Another aspect I think that is relatively missing in the in situ and operando electron microscopy world, and I think there's room for students to think about, is how we can integrate artificial intelligence to deal with large data sets and big data that we are collecting by doing in situ TM. My students collect gigs of data from doing in situ TM, and it's always challenging to analyze, go back to the data and find out if we are missing any information or important electrochemistry or not. So I think there is more opportunities to integrate artificial intelligence with the type of work that we do at atomistic scale, and I encourage every student that is in this meeting or others to consider their incorporation into the future of these studies. That's all I wanted to share, Jordi. I like to leave it open for students to ask questions, or if there's anything else that would be insightful.
All right, thank you, Reza. I will note that you're starting to see some of the messages kind of pop up from different directions, but telling you some of the same things, even though the systems that they're discussing specifically are quite different. So
okay, sure.
we've been hoping to emphasize in this program. The idea of machine learning has also come up in data analysis and so on. Okay. So it's time to discuss, and I've seen already some discussion in the chat, but I'm gonna still do some call outs based on what I've seen. Tommy, you had a question this morning about measurement of local electrochemistry in systems that were not biological. Did this presentation tackle, or these opening statements tackle that? Do you have a follow-up question that you'd like to bring up?
Yeah, definitely. I think this presentation really showed in many ways a lot of the ways different electroanalytical techniques can apply to a variety of systems. But I guess sort of a general question I'll put to the panel is, how do you think about choosing the right analytical technique for the phenomena you want to study, and I guess at the scale you want to study it?
All right. Who wants to tackle that? That's a good one. How do you choose which technique to use, basically?
If you have a 2D system you trust, I'm all for using the scanning probe work. So we've actually adapted pyrolysis of a benzene onto quartz slides to make a very high quality carbon. In fact, pull up the papers, you'll never buy glassy carbon again. And it's even better than graphene in the sense that it's oligophobic. It does not pick up hydrocarbon. So then you can start asking questions. What happens to a probe electron transfer rate if I sprinkle a little pixie dust on it, gold nanoparticles, palladium nanoparticles, or I form that pyrolytic carbon with a heteroatom like sulfur or I do some oxidation of the surface to get the carbon oxygen. So that gives you a classic 2D system that's far easier to bring in our very well developed in situ probes, operando probes, and the scanning probes. So we definitely like Kelvin force microscopy as well.
Yeah, I have a follow-up on that. So I think it's always good to think about, I mean, we are talking about electrochemistry, right? There's so many different examples. And think about which process you want to study and what it does, for example, to your electrode. Let's assume I want to look at ion intercalation into a specific electrode. Find out what is known about what property of the electrode is mostly affected by the ion intercalation. And that determines your method. If there's huge volume changes, right? Yes, scanning probe, local volume changes, sure, but there are electrodes which don't have that, so it would be the wrong method, right? Other materials might be very robust to the electron microscopy beam, right? And then you're like, well, let me try that. So I would look at like, what's the consequence of the process you want to study, and that gives you a little bit of a hint of where you should look.
I also would like to add that sometimes there is limitations with the type of specimens that you are interested to explore. And you know, from my side of that are doing electron microscopy, we always are limited to the thickness of the material that we can explore. So if you deal with samples that are very thin in terms of thickness, nanoscale, then maybe TEM would be a good approach to study some of the electrochemical reactions. If systems are maybe interested on the surface or so, maybe some of the work that involves surface probing techniques will be good. So I think some of that sort of analysis also depend on what system you're dealing with. And as Nino mentioned, you know, what information you eventually want to obtain. So that information, you need to screen the type of techniques that can provide you that particular signal and that particular information that's going to be helpful for you.
Yeah, I don't have too much to add to that, except also, you know, to think about the intention, right? Is your intention to measure some physical parameter that where you have the flexibility to transform the dimensionality or the shape, or even, you know, to an extent the layout, right, of your sample? And I think that this is, you know, it agrees with what Debra mentioned earlier, right? If you have the flexibility to just like think about a flat electrode, then go ahead and do it, right? And so but if your intention is to do an operando experiment where you really want to know what happens in that, you know, convolved 3D structure and everything, then, you know, I think that determines very importantly the scope and the type of methods that you're going to have available. And then, of course, you have to ask yourself the other typical questions, right? The one that Jordi loves to ask always is, you know, where in this triangle of time, scale, and performance you are, right? And what are your needs? And so that really is so important.
All right. So Julie, I know that you've been interacting in the chat. Do you have a follow-up that you want to add to what's been discussed already? Did you get your question answered?
My question was mostly answered. I guess to follow up, because those who didn't see in the chat, I kind of just asked, like, if we're looking at like a local scale, how are we translating this to like a full battery, right? I guess, like, if anyone else has anything more to add, I was just curious on, do you think there needs to be more coupling of like looking at local and these analytical effects and then also running in cell, or do you think that's like too hard, too easy? Yeah, I guess if anyone else has anything to add, but I appreciated the chat.
The way that I would amplify that is, you know, if you're going to use these exquisite techniques, how do you go about exploring the phenomena in Debra's architectures that are so sophisticated? You know, how do you even start there? How do you know that if you measure something out of that architecture that is representative of the architecture as opposed to a minority species?
I think that's the point, Jordi. You could find something that is really interesting, but may not be relevant to your technological electro reaction. And Nina can certainly discuss that with respect to microscopy. You're always, attracted to a feature that may not be telling you something about the overall material, but is really cool. But where the local information that are coming from the more 2D electroanalytical operando approach could be, okay, this is being very either stable or active. How do I make that expressed into the technologically relevant electrode structure? So to me, that can inform, and I'll give an example of that. In the, we all know that ruthenium oxide is one of the go-to high performance pseudocapacitive materials. But it wasn't till we did a pair distribution function analysis of that, 20 years ago, that showed that the high performer is hydrous ruthenium oxide that has always been, if you will, an inorganic block copolymer. It has nanocrystals of rutile RuO2, which is a metallic conductor, where all the surfaces are seeing disordered crap. So you've got something that's very good at moving protons sitting right on top of the thing that's moving the electrons. And the more water you take out of the structure and more rutile it gets, the lower the farads per gram of RuO2 you can obtain. So that is indeed why we've moved to things like these 3D carbon structures painted with important electroactive storage catalytic species, because that's what ruthenium oxide, what nature was doing all along to make the optimally performing material. So if you've got that kind of insight, that makes you write a new cartoon. And that changes all of your thinking. So I like to see that sort of that, back and forth between understanding a real material, and that's where many of the new techniques help, transforming it into your insight in 3D, but still remembering to slip back into 2D to, if you will, validate and get more knowledge. Always question your assumptions about, is this heteroatom really acting in a plus or minus effect with my heterogeneous electron transfer rate constant? Sulfur, for instance, in pyrolytic carbon, not so good if you're looking at very ferrocyanide and nitrate aqueous electrolytes. No chloride, because that speeds up your electron transfer rate. But if you use that sulfur, which is thiophene-like, to specifically absorb a little gold pixie dust nanoparticle, then you can start to influence your catalytic reactions. So to me, you keep everything on the plate.
I'd also like to say at this point that, none of us as researchers are superhuman, right? It's very difficult to think that you personally, right, are going to be able to make the material, develop the technique, understand the technique, and simulate the technique, and understand everything that you need to do just in time to deliver your dissertation, right? Research just doesn't happen like that. And I think that some of the most exciting research that at least that I read and that really gets me excited is when you have collaborations, right? And so I think that being able to pair up with researchers that are mainly dedicated to the analytical side or to the materials characterization side, however you want to see it, is important. So designing some of these experiments is not trivial, and so kind of like, always have opening these dialogues so that you can find folks that can help you with it is really critical.
I will say that this topic of phenomena that are happening at very short scales and how it gets translated to a system just keeps, it's a running theme basically through the different panels that we've had, again, with changing topics, but it just keeps coming, this translation.
To follow up on Joaquin's point, Jordi, I've often criticized the Department of Energy because to me, it's the department of everything but energy. But I think the Energy Frontier Research Centers have actually moved the ball down the field. in the sense that they're creating interactive teams that are addressing important energy technologies, which is something that was sort of discouraged by DOE for a long time. So to me, the EFRC investment has been both important and impactful.
All right. So Joy, I have you next on my list. You want to add thoughts to the discussion that you've been having back and forth?
Yeah, thanks, Jordi. So yeah, I wanted to ask a little bit more on the interpretation of the data and the assumptions and things that convolute the data. So kind of going off of what Reza was saying as well about new techniques for analyzing this data. And so I'm curious, when we go from the data to some sort of physical interpretation, we have these models, and I'm curious what kinds of assumptions you all think have traditionally gone into these models that might be challenged in the near future. And also, again, like what kinds of convoluting factors you think you have to take with a grain of salt when you're interpreting these kinds of results. Thank you.
So how do we know what we're measuring, basically?
I think it goes back to something which was just said in the question before, that validation is critical, which you can achieve by working in a team. Like the more you know about your material, the better your insight will be. I think basing interpretation on a single experiment is rather, you can be wrong. And so the more you can collaborate in a team where you have people with complementary techniques, the better you will fine-tune your data interpretation for yourself. And it's the validation is a really important process in this.
I think it's also important just to question the dogma our forefathers, and they're mostly fathers, have handed down. So in the, in the case of that zinc intercalating into the layered materials, that was sort of the expectation. But the more you understood and characterized the system using multiple techniques, the more you had to say, this just is not dominating the electron storage event. So it's always important to question dogma, to in essence say, you've told me this, but is that really so? So back to the ruthenium oxide example, you'd be reading things that RuO2 0.2, 0.3 moles of water was a metallic conductor. And that always bothered me. It was like, why is that a metallic conductor? Why with something that has that much water in the structure is it a metallic conductor? But once you understood from the PDF analysis that it was an inorganic block of smaller than X-ray powder diffraction can see crystallite RuO2, 1 to 2 nanometers, that was moving the electrons. And then it made sense. Yeah, we could slosh water in and out of that system, but it still has the characteristic of a metallic conductor. So these things that you read that seem to be accepted wisdom, but strike you as something's a little wrong, is actually a good starting point to ask better questions.
I tell that to my group all the time. If something doesn't strike you as reasonable based on what you know, it might not be reasonable. There's a high chance that it's not. So this is another good takeaway. Wessel, I have you next. You had a few questions. If you want to ask them, in a stream, that's totally fine.
Yeah, I have two different questions. One's describing the system, mostly related to kinetics, and then one is related to carbon loading for your material. So related to kinetics, I know Debra Rolison said that, B value is an abomination. And for people that don't know, it's a relationship between peak current or a current at a specific voltage and how that changes as a function of the sweep rate and everything. I know you do the 3D boat analysis and everything. Are there other techniques or suggestions you may have for describing a system and describing those kinetics and everything in an honest and reasonable way? I'll just start with that question.
Even before, the world jumped into energy storage with both feet, certainly in the area of microelectrodes and other things where you were pushing the kinetics rate much faster than you could typically address using voltammetry. People like Israel Rubinstein, who is unfortunately long dead, were bringing impedance in. So if you've got a well-behaved system, that's certainly one easy, in-lab tool you can start to play with. Brian clearly was thinking deeply about these problems before he died. So I think there's a lot of reason to do what he's done and what we've done by looking at the capacitive part of the impedance curve as a function of potential, as a function of frequency. I will point out that in the early chemically modified electrode days, that was typically what one did. One looked at the peak current, not the current along the whole potential scale of the voltammogram, but the peak current. And as a function of where you fell as a function of sweep rate, you could see a slope of 1 if you had surface confined, i.e. no molecular diffusive transport, or 0.5 if it was class 6 semi-infinite. But most systems, particularly when you started to go to polymer modified electrodes, fell between. And that, going back into the 60s, work done by Charlie Riley, Fred Anson, you're looking at finite diffusion. And when we're making our battery materials out of submicron systems, we are in finite diffusion regimes. So at that point is, well, what is surface? Is there semi-infinite? Well, it depends on the time scale you're trying to draw the electrons out. So if you're living on a B analysis, to me that is bogus, because it's not helping you think about the real system.
And Wessel, I would add to this that, that's a really fantastic question. And I can tell you that I'm part right now of a collaboration with some other people that you've seen in this program, with Professor Veronica Augustin particularly, right? Where we're actually asking some of these questions, right? Like how valid is it to use this type of models, and how does geometry, thickness, surface processes can affect, the interpretation. And so, totally on board with this. And I think that there's a good amount in here that understanding quantitative, Debra was talking about this finite, right? And so simulations, there's a bunch of tools nowadays, right? That can facilitate the interpretation of experimental results in ways that were not possible 20 years ago, precisely when many of these concepts that Debra was talking about were developed. And that nowadays you have them at your fingertips, right? Developing a COMSOL method, for instance, to understand the boundary conditions of your particular problem can be extremely enlightening. And so that's that's something that, as a skill, I encourage my group to do, like, pick up the simulation, be able to describe the specifics of your problem, right? And not only rely on prefabricated analytical expressions.
Okay, I have Alessandra next in my list. Alessandra, you want to take the floor?
Hello, everyone. I am a huge aerogel geek. It's what brought me to chemistry and electrochemistry to begin with. And I had a question related to putting electroactive materials into the aerogel. And I have a little bit of I don't want to feel as though I'm giving you attitude, but I don't understand why you would want to paint or glue electroactive materials just onto the surface. Wouldn't you want them to go into the porous material? What's the point of just using the aerogel surface? Aren't you losing the power?
Those are lessons one can take away from the zeolite world. So they often will put nanometric metals or coordination complexes or some kind of a chemical intermediary inside the porous crystal. And of course, you're working with a microporous entry into what might be a super cage, where you might have a nanometer, or maybe a little more than that. So you could support a nanometric type of thing, but that starts to block your ability to move molecules in and out. So anything you do to interrupt a 1 or 2D porous system will totally kill your flux. 3D, not quite so bad as long as you keep the loading low, but is that really what you want to do? So there can be some instances where you may want a particle. So in our early work with trying to turn silica aerogel, which is an electron doorknob, into a metallic conductor, we wanted to paint it with ruthenium dioxide. So we had a number of ways to equilibrate precursor into the aerogel, and well and good. You got a lot of surface area, you got a lot of control over the Langmuir isotherm. But the minute you converted that precursor into ruthenium oxide or ruthenium metal, surface energies had it ball up. And that's not what we wanted. So we actually developed a subambient temperature electroless way to paint the ruthenium oxide. And we've had a lot of studies on that. Cool fact is, at a few nanometers to maybe 10 or 20 nanometers thick, it is a transparent conductive oxide. So, I mean, there's just, you know, the more you learn how to do non-line of sight chemical and physical modification in things like aerogels, where you've got really tight quarters, it just translates all over the place, even if you step back and go 2D. But if you really want a little ball, our approach is to actually pull it in when the solid particle that's going to gel and create the network, just before it gels, it will sweep things in. So we've put things that are a nanometer in size all the way up to a millimeter size, and they're retained within that supercritically extracted solid. So there's it's a play box. You can just we've turned high school students loose on this, and they just have a fine old time.
I just realized that Wessel had asked for more than one question, so I'm gonna go back to him real quick. Wessel, go ahead.
Yeah, it was related to those aerogels and describing it where you have essentially your active material loaded onto carbon. I was wondering if with that system, you're kind of ignoring the electronic transport capabilities of your material in of itself, and kind of losing the insights you might gain into, you know, different modifications you might do or architectures that might affect that. Yeah, go ahead.
That does matter. Carbons have a wealth of electron conductivity. And the classic carbon aerogel, which is a condensation polymer that's pyrolyzed, very oxygen rich, only modestly conductive. You're looking typically at a 1/10 to 1 Siemens per centimeter. And that's not conductive enough, which is why when we went to doing the sol gel chemistry in carbon fiber paper and controlled our surface energetics such that these polymer strands crossed the voids, you know, tens of microns. So it wasn't just wrapped around the fiber, it actually created a foam within the fiber paper as the jello mold. That's when you get ultra high surface area. That's when you can change your void size based on the fraction of organic that is in the sol. So we've been able to tune those up over 100 nanometers and down to 5 nanometers. And it depends on application. You know, do I want ultimate capacity, but I'm going to have to go slow? You go small. If you want really fast response, you are going to go to the wide mouth pores. And we've got one formulation that kind of gives you the best of both. And we've published that, you know, a long time ago. But those are the things you can start to ask. You always think of it like a 3D current collector. And you'd like that to be as conductive as you can get away with.
Weston, any follow-ups?
No, that's super helpful.
Covered everything?
Yeah.
Okay, sounds good. So next we have Wan Yu on the line that also wanted to ask a question to the panel. Wan Yu, the floor is yours.
Yeah, I kind of asked a similar question yesterday in the solvation panel, because it was brought up in the solvation panel that it has been more and more obvious that the solvent and solvation has been playing an important role on top of the cation in the energy storage field and probably also in catalysis. So is there a known local technique that can probe the solvation at different places? Because it shows also that the solvation kept changing when the ions is moving across the bulk interface and in the electrode. So is there a local technique that, or combination of technique that can tell us about the solvation?
All right, love that. Connecting one panel to the next. So what's your take? How do you measure solvation? Yes, we spent 90 minutes yesterday telling them that it was a very important event. So how do we go around understanding it?
to me, if we're thinking of water as the solvent, you get a lot of insight if you get into a competitive regime. And that can happen with ions that love lots of waters of hydration, but they're now living in a world where there's not a lot of solvent around. So that's when you can kind of see who gets to hold on to solvent. And I think that's a huge part of what's known as the hydrophobic effect in biology. Who wins out in terms of keeping water around that ion or that molecule or at the surface? And electrochemistry should be a good way to do that, but we're going to have to perhaps work with vapor phase equilibrated systems rather than immersed in liquid electrolytes.
Yeah, you know, we've wondered a lot about that question as well, because in principle, if you have you know, processes involving the desolvation of ions at model interfaces, doesn't necessarily need to be at any particular interface that you're studying, that could be informative. I mentioned, for instance, our mercury probes, where we can look at lithium ion dynamics locally on an electrode. We wondered for the longest time, for instance, if you could actually detect changes in solvation based on the intercalation, on the insertion potentials, right, of those, the amalgamation potentials of those ions on interfaces like that. And so I think that there are many sort of measurements of that type that could inform about solvation, but I don't think that it's that it has been a problem that has been widely picked up, at least from the electroanalytical community. And I think that it's a problem that is definitely worth looking at. And so, yeah, I mean, you are right in asking what are the types of techniques, right, that are available. Other than that, of course, I think that there's a lot of techniques based on interactions of X-rays and neutrons, right, to look at the local structure of different species that are in solution. But of course, translating those into a reactive form, like, you know, figuring out what happens at an interface, for instance, that's still something that I yet have to see, right? You know, how it could be applied.
So my take on that is, I don't know. When you know that I don't know the answer, but I was always thinking, like, how could you do that? And coming from pseudocapacitance, the technique of choice to look at it at the microscopic scale is EQCM, right? So I think it would be, going forward, very interesting to see what would be a local analog to that. And you can think about, in EQCM, you're looking at mass changes, which are measured through mechanical vibration. So, right, that could push you towards local mechanical property mapping. So I was thinking about that question, if AFM if there's any way you could develop an analog to EQCM, which you can apply on the local level. But I've never tested it out, but it would be very interesting for someone to do a parallel study of EQCM and AFM and see if there's information which overlap. And so you could perhaps interpret it in the same way as EQCM, looking at like mechanical resonances locally with the AFM tip. But yeah, nobody has tried that out.
When didn't you bring up EQCM yesterday? Was it you?
Yes. Yeah. So the one we know so far, as the panelists brought up yesterday, it was a bulk technique. Right now, it's demonstrated by combining EQCM and NMR. It's possible to get more information out of the solvation, because NMR give you chemical information and EQCM give you overall, so you can subtract the cation and know the solvation, but it's kind of an indirect way of doing it, and it's a bulk technique. So we were wondering if there's a local one. And of course, I'm from AFM perspective, I only know what AFM, specific part of AFM can do, not all the, not including the SECM, SICM, just a specific part of AFM can do. I was just wondering if there are something else that can, work together.
I think what Nina is telling you that you should go ahead and develop the AFM equivalent of EQCM. If you have right. AFM and EQCM experience.
The next generation should develop that.
Yeah, I think Nina is bowing out.
But work on that. Thank you all.
Reza, do you have any thoughts on looking at solvation from the perspective of a TEM?
You know, in microscope, if things are in the liquid state, it would be very tough to interpret the signals. But if that solvation can be somehow interpreted in terms of any reaction product that is forming and stable under the electron beam, then I think, you know, electron microscopy could be a technique that maybe help, especially with, for example, yield signal. We can look into the bonding of like lithium or other elements if we can do things in a very low sort of dose level. But in the liquid state, I think you know, things are very dynamic. That it's going to be much slower than the resolutions in the microscope in terms of time resolutions that we can capture proper sort of events. But I think that's interesting overall problem, and maybe there is way to do things in cryo or something like that. So that's you know, with the development of cryo-TEM and their incorporation in microscopes, maybe some can take a look at those as well.
So notice how you're getting an answer that says this probably not something that you can, you know, no magic tool that's gonna give you that direct information today. Maybe you can develop one, or some of the thought process that you've been hearing, especially now from Reza, is, well, there might be workaround. You might not be able to measure solvation directly, but you can measure a proxy for it. That if your model tells you that if that proxy is there, solvation is X, then if you measure the proxy, then you can be confident that solvation is X. So that's another way of working around a complicated research problem, that it's just as valid as getting this beautiful tool that measures everything you want. I wanted to go to Michael because he brought something up in the chat that I had a note that I wanted to bring up if it didn't come up again. So he's giving me the opportunity not to have to do it. So Michael, why don't you take the floor and elaborate?
Okay, thanks. Yeah, so I'm a researcher in lithium batteries. So I kind of interpret the question through the lens of a battery chemist. Anita brought up how individual redox reactions might affect the outcome or the kinetics of a reaction that happens adjacent to it. And kind of brings up lithium intercalation in a metal oxide being a potential example. And I think as a battery chemist, I come from the perspective of, if you have capacity loss in a battery over time, you're usually going to attribute that to things like you're consuming electrolyte and forming interfaces at electrodes, or you could have dendrites that short circuit and become disconnected from the current collector. So I guess my question is, do battery researchers need to, sort of pay more closer attention to these types of kinetics issues? And, you might be able to take all this lithium out of an intercalated material on the first charge process during when you're recycling a battery, but then you won't be able to put all of that lithium back into it. So I guess, do we need to pay closer attention?
Well, we already know that's true. So, your silicon anodes without extraordinary other chemical physical modification have such a mechanical catastrophe that it's very hard to get all that first initial capacity back. And it's understood in the military. When you're out in the field with a BA 5590 radio and you've got the battery running your radio, and that's either lithium sulfur dioxide or lithium manganese oxide. In the field, the slow, steady drain to give you a lot of energy density is not how it's used. There's a duty cycle. And often they will try to get power out of that system, including modifying some of the safety features to get that power. And that causes mechanical strains and stresses that can affect your ability to talk to the active material that's there. So in use, the warfighters find that the rated energy density from the manufacturer, they get about a third of that. And because they need redundancy based on the energy required for the mission, and they know they're a third of what they need, and then there's the redundancy, they can be carrying 9 times the number of batteries over what the manufacturer said the energy density it would deliver actually is. And a lot of that is mechanical. And that's why if you're working with a better wired system, you often are not, it builds in innate power. And that's what we're always finding in these 3D systems. You've got a way to get power out. And that's true for the zinc sponge as well. It doesn't have to be nanometric. If you've got good wiring, you can actually get a battery system to be hybrid in its performance. And you're not detracting from the bulk of the energy density that's innate to the active material. So we just, again, need to be much, much smarter. You know, we've had, a century and a half of, fuel cells and over that of batteries where, we've gotten away with making very cheap electrode structures. And, it's somewhat amazing they work as well as they do.
Just harping on that notion a little further and taking it a little further into the unknown, basically. This idea that we tend to think about reactions and competing reactions at a bulk level, and it's the electrode falling apart. Is there a competing reaction that is slowing down the reaction that you want to use for whatever purpose? Is there a degree of freedom there where what's slowing you down is basically reactions that are, say, two particles that are stealing current from each other? Or is that what you had in mind, Nina? Is this, or is it the concept of competing reactions that you were, purely, one reaction stores energy and the other one is a decomposition reaction, and so you can have a decomposition reaction? Yeah,
I like that picture of stealing from each other, right? Or there's also there's an interesting paper where they did the experiment where they had two identical battery cells, and on one they put a mechanical pressure on top, and they measure the voltage difference between that, and it comes back to you have equivalent energy electrochemically and mechanically. So if you have a lot of mechanical energy, which is like a loss, then it affects your local voltage as well. So if you have an inhomogeneous ion intercalation and strain development, you will also have automatically voltage inhomogeneities, like a local, think about like a distribution of electrochemical potential across your sample. It's another interesting question. How do we even measure that? Like your CV curve gives you one, but I think there's in reality a distribution of them, and that then goes to the stealing, right? Like if there's like a slightly higher effectively electrochemical potential in one area, it will probably take also ions from the surrounding areas at a lower potential. I think there's a lot of interesting questions around that. This idea of competing processes within the electrode.
How would you, and this will take us back to Debra's architecture, but any thoughts on how one starts interrogating? So we're kind of saying that this is an unknown thing, but it's probably going to be something that happened at the nanoscale. How do you start? How do you, when the architecture is so complicated, how do you even know where that may happen so that you can go and put your probe there and look at it?
That's a good question. The point I wanted to make is that I think you should strive for getting rid of the heterogeneities, right? So, for example, find a way to, let's just say you have ion intercalation resulting in a lot of volume changes in the 2D material. Can you incorporate pillars so the ions can go in and out freely without modifying the volume of your electrode any further? Now your electrodes don't have to work this mechanical force, right? And there's no losses. Then of course you cannot detect it using strain-based method anymore, so you're out of work. But I think you should think about how can we get rid of these heterogeneities in the long term, which I know doesn't answer your question, but it's an important point.
Well, it's a good solution, though. You don't have to worry about it, right?
Right.
Definitely.
But I think our zinc system shows the promise of creating not a perfectly uniformly reacting electrode, because we're all realists, but close to it, and that's what the post-mortem ex situ microscopy demonstrates. You've really got a very consistent type of retexturing over a high surface area. And even though we're working in the micron size of particles and voids, there's a factor of at least 300 per cross-sectional square centimeter. And that's why it is so hard to make a dendrite. Locally, you can never broach the critical current density to form a dendrite. And if that electrode is itself more uniformly reactive, you are not imposing non-uniformity on the countering electrode. So in the silver zinc system, the silver is often the bad actor because of the non-uniformity at the zinc. You've created high flux lines, high current distribution, and that starts to spall off silver colloids. Well, we found without doing any of the extraordinary efforts people do with separator systems and surface treatments that we could just take a standard silver oxide powder composite counter electrode to the zinc sponge and not make dendrites and get 50 cycles, 100 cycles at relatively high rates, because if one electrode's behaving, the other electrode starts to behave better as well. So these are to me, it's like, yes, I want to understand what are the important either catalytic or energy storing entities, how ordered or disordered or fluxional do they need to be? And then the thinking is, okay, let's create an architecture that is itself as uniform as we can get in the real world. And that means you got to have good electron wiring. And if you're not imposing, if that can get a power delivery, then you're not imposing the mechanical forces that really mess you up in terms of the amount of active material you can talk to. So our silver zinc, we can get a silver standard electrode, no special separator system versus the sponge. We can get a 17 C rate out of it. So you don't need electrochemical capacitors.
Right, that's the dream, right? You know, the best of capacitors and the best of batteries in one device.
The star on Nina Dragoni.
Right. We are at 2:30 according to my clock. So I am going to make sure that I stay true to my promise to respect the panel this time. So I'm going to close the panel here. I think we've had a very good discussion again. There's also another event that starts in 30 minutes. And I want to make sure that all the attendees have time to freshen up and be ready for another set of discussions in a different format, but discussions nonetheless. So thank you, Nina, Reza, Debra, and Joaquín for making some time to discuss with us and share your thoughts with us. Thank you, everybody, for being here. And we start again at 3 p.m. I'll see you then.